Hello and very welcome to our tutorial series on Verilog. In this module, we are going to explore. Okay, we have written numerous cores in Verilog for different design, such as inverter, logic gates, tri-state buffers, simple buffer, and we have explored different modeling techniques such as data flow, structural or gate level modeling technique, and also the behavioral modeling technique. So if you are new here for the first time, and then you can refer back to our previous modules on that, writing a Verilog code for that. Now you can see this empty blank screen where I have opened up the browser. And in this browser, what I want to do is find some free tools, open source tool, or in other words, a free tool for compiling my Verilog code. After I write the code in the compiler with proper syntax, keywords, I would be interested to use a tool or a software or EDA, electronic design automation, used for Verilog compiling, Verilog HDL compiling, and then simulation. And next step is also synthesis. But right now we will only talk about compiling it. So obviously there are commercial tools available, commercial softwares available, but we are interested in, if you are students, you cannot afford to buy those expensive softwares to write the Verilog code and compile it to see if your design is as expected, the digital design. Even if you are not student, let's say you are a professional, still the proprietary tools are quite expensive, and therefore this open source movement is going around by few entities around the world to promote this open source environment to make, to break the barrier for the cheap design. In almost many countries in the world, that kind of initiative is being taken over and pushed forward. So how do I find out? I don't know what tools are available, right? On the browser. So in the browser, what I would be interested in typing something, some sentence which will help me to find out the free tools available to compile the Verilog code. Free tool, uh, a Y label to compile Verilog code, and of course the same tool can be used. Okay, we can also write some title like here, cloud based, so you don't need to download and install them, right? So it's just very simple. Okay, you can also call it as open source, or simply just keep it free, free tools. Okay, and so click enter and look what you see on this website. You basically can see that there is this website, and where free for open source projects, right? And then there are like open course EDA tools, electronic design automation. So Icarus Verilog Simulator is one such tool, is used for Verilog simulation and synthesis. Verilator is a free Verilog HDL simulator. Then you have GHDL, VHDL simulator. This is not a Verilog simulator, rather it is very VHDL simulator. Know the difference. Then you have C to Verilog. So if you know if you are proficient in using C language, you can actually do the Verilog translation. Then there are all this. Then you have this website, you can go to open course EDA tools. Then there is this, you can find some questions, answers here. Okay, here is this one, like free and simple Verilog simulations. So here it is written, we will use the following software to code, compile, run, and visualize our Verilog files. Is like that. Okay, so you can just simply click one by one here. online Verilog compiler. Okay. Then there is this EDA playground. You can actually, then there is this online tutorial, online Verilog compiler. So there are plenty of options available. And there is this community. You can use which Verilog simulator to install and all that. So how about, let us click here, online Verilog compiler. So we'll see what it does, but before that, just go back and read. It says this online compiler provides the comfort to edit and compile your Verilog code using latest version Icarus. Here, this tool is being used. Okay, so let us click here. Once you click there, what you can see is this window open. This is an online Verilog compiler. There are few buttons here such as execute, beautify, share, and then there is this source code. We are in this window. So obviously, you see that slash star and then star slash in between these two. Whatever you write is regarded as comment and it is ignored during the compiling phase by the compiler. Then we have explained already how we basically write your code. You already, you always have a module and the name of the module. Here the name of the module is MAIN, main. And when you have a module, then you have an end module. And in between module and end module, you have to write your code, define your hardware. So obviously, you can see that. So what I'll do, I'll use this initial. This is a keyword. We'll talk about this later. And then you use begin and end. So in between begin and end, you have used this special keyword display with the dollar sign. So that is used to write display something on the when you execute and compile this code. So in the parenthesis, you have written hello world, and then you use another keyword finish between begin and end, and that's my basic code. So here what you need to do is you will click the execute button and see the output got printed here. It says that hello world, right? So you actually can see that hello world has been printed out there. Okay, so let me also explain you more steps, what more you can do with that. Okay, so what we see here, we have successfully compiled this code. That's it. There are a few other options, like when you click on them, you will see what they do. If I click on beautify, there is nothing happening. Here you have a possibility to share your code. So it's like there is something you can, if you are a student, you can share it with your teachers, classmates, friends, or even at your website. Okay. So you have to just write, enter this captcha, and then you get a shareable link. Let's try that. 63E6AT. And once that we do, we just click here and you got this link, right? So you can just click here, copy, and share it with anybody you want. Okay, that's it. So that's your code. So that's your perma link. We just close it and we come back to our original window here. Okay, so that's the source. If you need any help about this compiler, you can click here, and here you are asked to try this online Verilog compiler to edit, run, and share your code online directly from your browser. Okay, so basically you can edit and compile your Verilog code using this latest version of Icarus. So that's your tool. The software is Icarus version 10. Okay, and how to use this compiler, as I showed already, you write and execute. So write your program or paste it directly under the source code tab here. You just paste. If you already have written your code, for example, I want to show you, let's say I have this code for the inverter. in two different styles. So inverter, we know that this is the logic NOT gate. Output is complement of the input. And I have used two styles to model this inverter behavior. So one is data flow, second is gate level. I have explained that in our previous model, how to understand what is data flow style, what is gate style. So if you are new here, you are encouraged to refer back to those modules. Okay. So again, module and end module. So name of the module is INV in my case. You can write inverter or not gate, something like that. You can't write not because not is a very long primitive. So you just give some full inverter, something like, or simply INV. Okay, or simply say my logic or my gate, something like that. Then in bracket, define your output and input variables. My output variable is Y, input variable is A. And then you write your output wire Y, input wire A. You can skip using the word wire, keyword wire. You can simply write wire Y, output wire Y, input wire A, or simply output Y, input A. And then use this statement, assign Y equals in bracket not of A. You don't need to use this parenthesis, but for more clarity, you can use that. Don't forget to add the semicolons after each code right here. So you have this code. So let's say I want to copy this code. Just right click, copy it. Now you want to come back to your screen right here. So what you do is like select it, okay? Press the delete button on your computer and then Control V. That is your code. Okay, so if you want to know if you have written this code very well or not, just click the execute button and see if there is an error here. uh, there is nothing like here. Okay, so obviously the code has no error, but for example, let's say you have something related to something like this. Let's see if it goes or gives you error. Okay, or maybe something like this. Look at this syntax error. I have typed this one here. So it is syntax error and it is showing that operand of unary is not a primary expression. So the operand is not good. So close this, again click execute. So this may be acceptable, but I don't know why I should have this one. Okay, so for example, if you write y equal equal, so again you have a syntax error. There is a continuous statement, continuous assignment cannot be defined like this, so you just have to keep it as original. Okay, so now it should be okay. So whenever there is a syntax error, the output terminal will reflect it. Okay, so what about the second style of the code module? Here I have used the Verilog primitive. We have explained this in previous module, how to write the gate level modeling. So come back to the screen, select this, press delete, then Control V. Here I would press enter. So this code reads like this. It's like I'm describing the inverter module. Name of the module is INV in bracket output input variables. Here output and input are defined. These are ports actually. And then you have Verilog primitive not. I'm instantiating the not gate by calling the Verilog primitive directly. Not gate one in bracket output precedes the input. Don't make it a comma y, otherwise there'll be error. We'll see in a moment. And then there is a delay of 10 time steps, time units of the NOT gate. When you have a logic change at the input, it will take 10 time units to reflect the change in the output y. So click here, you will see that there is an error. So that's a good thing. So you have invalid module item. So here is a good example what went wrong. To understand what went wrong, You can see that. So there is the model inverter, output, input, gate, y comma a, and module. So you have to understand like where can be the wrong thing. Okay, so main v of 7 here at this, because you have used the time units but you haven't actually specified the time here. In this case, okay, you have to write the define or declare the time first. So let's say we'll remove this and then may execute. Now look, there is no error. Okay, so as I said before, we'll see if the input can be defined before the output for the Verilog primitive. Okay, so now here the input precedes output. Let's see, there is no error, so it is also acceptable. It shows that it is acceptable. Okay, so basically this is like only checking the syntax. Okay, this tutorial only checking the syntax, so hope that is going on. Okay, so let's say you have double comma here and we'll see that, look, logic gate port expressions are not optional, one error during exploration elaboration. So this is how your code will be executed. Okay, so that's going on well. Let's see more what we can do here. Well, what is now to be seen, there are some buttons here, learn Java, then compilers. You have different compilers, so we are using Verilog compiler actually. Then you have a project, open new projects, you can save this project, you can share this project with somebody, then edit. And here are the buttons like copy paste, redo, undo. Then you have a settings where you can change the theme of this one. So let's say I have used the first one, so look how the changes takes place. Look how the changes takes place. Then you have a font size, so let's say I've used 12 point. So here is the 12 point, but I want to have a bigger, so maybe 16. I got the change here. So again, like tab size, you can choose, uh, and so many settings you can do. Then there is this like editors, A, V. Okay, so you can click and see what things go, how things go. Okay, so I hope you found this module useful. Let's say again, let's change the theme to ellipse maybe, or maybe GitHub solarized. Okay, that was the solarized again. So this one, this looks like fine. Okay, how about we execute different code again? I have another code, for example, um, let's say right here, this code. We'll see if there are errors here, because now here we have. So copy and then go back to this, then just select this, press delete, then control V. Now this goes very well. So I have used this code, execute, but there is no error. So it says that no top level models and no dash S option. So, well, it looks like we have this code and it didn't really showed any error. Okay, so that's how you can use this compiler for writing your course and execute. So hope you found this model useful so far. How about we click this back button, leave the site, and now we have this second one, EDA Playground. Uh, so we'll see what it does first. It says that it lets you type in and run the HDL code using a selection of free and commercial simulators and synthesizers. Okay, so there is like both options here. Okay, simulators are there. So we have clicked this and we are loading this now. So it's going on. So let's see, and it has come. And now it is asking you to kind of, let's say we don't want this. If we can without login, we can do it or not, we'll see. So close it, and you can share the code also. Okay, so let's get started. Maybe you need to log in here, or maybe just, so I will log in here in a moment. You just click here on the Google and you have to use your email address. Okay, so we'll after you do that, you will be able to access the background screen. So let's see how we do it. I have done that. I have logged in, and now look at the screen. I have got this screen here. There is a webinar also, know-how webinar, and then that's about to learn common mistakes in VHDL, like August 30. It says you are asked to register. Then what are the options here? New. Then if you see that, that means it will ask you to, if you click here, it starts the new playground. It's like that. So you got this test bench .sv system verilog, and here you have a design.sv. That's, so you need both actually. Not only you can code your design in this section, and then you can code your test bench in this section. And there is example of browse examples also. You have examples that you can do. Then you run the selected EDA tool. So if you are like here, then just select this, and then if you are here, then select this. If you click here, it gives you option to open a new file. So if you already have a file, just have it. Okay, don't forget about the extension. And if you click here, you also have the same one, create a file. So this is how the syntax goes. Okay, now it says that hidden menus, try zooming out. Okay, that's it. Then you have option of saving this. Whatever you write here, you can save that. Now look at this, languages and libraries. So you have test bench plus design. So there is a system verilog / verilog. That's the option you can select. Then you have VHDL, you have Python, C, everything. So let us stick to verilog / system verilog. What is this UVM and OVM? So click here and it will take you to some details of that. You can just come here to have a look, but right now we'll focus on this part only. So we have chosen here none. So it's a kind of libraries actually. So we'll select the default. Then there are other libraries, none, OVL, whatever. So you have to select between them. So we'll keep, we don't select right now. Now here it's options, enable TL Verilog, enable easier UVM, enable UV unit. Then you have examples here. But before examples, you have tools and simulators. So click here. And again, there is some information about tools and examples here. So we'll click here. How about you select this option? Look at this. When you click here, you have like, these are some simulators, but they are proprietary one. So you can choose whether to select them for your simulation or free one. GHDL, Icarus Verilog. And then there is a free synthesizer also, Yosys. Then there are programming languages, shells, out of support tools are listed. We don't want. So let us select Icarus Verilog here. Then you have a compile options. Then you have a run options. Then you have these options here, use run.bash shell script, open EP wave after run, show output file after run, download file, whatever. Okay. So now there are examples how to use it. So if you click each of them, you will have some examples. So let's say click the first one. So then leave, click the leave. And we'll see now the browser is going on, and here are the examples about, for example, here it is how to run the synthesizer. Then you have like TCL script. Okay, so there are various understanding here. Okay, okay. Now what you do, go back. Here it is, and then you have like Verilog. Click here. We want examples for Verilog, for example. So for example, a simple D flip-flop. Okay, so let's select this one and look at this. The code on the right side, I close this, and then test bench. To test bench is just like uh, another set of code to test your design. Okay, it provides inputs to the design and it collects the output to display. So how do you write the code? These the first two lines are the sentence, then you have module, and then you have end module. So name of the module is D flip-flop. Then in the parenthesis, you define input and output. So clock is input, reset is input, D is input, Q and Q bar, that is are the outputs. Then my input is clock, the reset is input, clock is input, D is input, and Q and Q bar output. Look here, I have defined it. Then you have to define the output register because the data is stored in this register, which is Q. And then you use the data flow modeling where you say that you use this declaration statement, assign Q bar equal to not of Q. And then you have this behavioral modeling actually style. So always at the rate in the bracket positive age clock or the positive age reset. Okay, so there are two inputs, clocks and a reset. So at the when these instances are triggered at the positive age of the clock or at the positive age of the reset, you write between begin and the end, between begin and the end, you write if the reset is asserted, then begin and the end again. Okay, so there are two begins and two ends. So this one begin, there is an end here, and for this begin there is the end here. So we are saying that if the reset is asserted, then to the asynchronous reset, when the reset goes high at the positive age, then q is equal to 0, set the output is equal to 0 and end it. Else begin assigned D to Q on the positive of the. So when the clock comes, whatever the value of D is 0 or 1, assign it to the output Q. Very simple. So it's a very simple code here. Now there is a this test bench to test this module. So what you do, module and the end module again. So it's another code. Give a name to your test bench, test. Then have the registers, clock, reset, and the D input are the registers, and the outputs are your wires. So it's like Q and Q bar are your wires. Then you are instantiating the design and the test, which is your D flip-flop. So you just call it here D flip-flop. So this name and this name should match. And then D flip-flop, DFF, capital D, capital F, capital F. And you have dot clock in the parentheses, again clock, then you have comma, then dot reset in the bracket reset, then you have comma, then you have dot d in bracket d comma dot q in bracket q comma dot qb in bracket qb and close, and then the semicolon. And then this is how the instantiation process is. Okay, you have to use this syntax, have all inputs outputs like that. Then initial is the keyword, special keyword, where then you begin the process. Then you are saying like dump file. You see somewhere here we had used this dump file. Where is the dump file? There was a dump file somewhere. Okay, so maybe for now we, and look at this time scale has been chosen to be 1 nanosecond slash with the resolution of 1 nanosecond actually. Okay, and we say, what we say is that dump file will be going to dump vcd and dump vars. This is, just ignore them for a while now, and then display reset flop. When we reset the flop, it will display like that. That comes when clock is 0 and reset is high. Clock is low and reset is high. And the D is don't care. X means you don't care what is the input at the D. Okay. If it is X equal to 0 or 1, then that makes sense. And then we say D is 0 or 1. And then you use display. Then display release reset. When you want to release reset, for example, when reset goes low and the data is 1, the D input is 1, display it. And then toggle clock. So just change the clock from logic 0 to logic 1 here, and then so this is how we are basically going to apply the stimulus to the circuit. First, clock is low, reset is high, so the output is like 0. Okay, this is how we have defined here. And then D doesn't matter. And then you have a reset. You release the reset. Reset is set to 0 and the clock is set to 1 thereafter. So that's how we do it between begin and end. Then task is display. What is to be displayed at interval of 1 time step? You have to display. There is this special syntax like D is to percentage mark 0h, that is D input, Q input, QB. D is the input, Q and QB are the outputs, and then D, Q, QB, end task, end module. That's it. So what you do here now, let's say right click, if we see that, okay, whatever, then maybe we have to click the run. And we have clicked the run and look, something is happening here and done. The simulation has finished. So maybe I want to show you how we have done that. Look at this. This is all your. So it says that, okay, timescale has been used like this, your design.sv, testbench.sv. These are the two name files. Then configuration file work, compile success, 0 errors, 0 warning. So good coding has been done. There is this information about HDL simulators, debugger design environment. Okay, and then there are some internal stuff, and vsim simulation has finished. So there are no more test vectors to simulate. So we've got few test vectors here to test this D flip-flop. So this is how we tested it. Okay. So writing a test bench is also an important aspect. Remember that. We'll explore that more in detail. So these are the inputs you see, T equal to 1, Q equal to 1, QB is 0. So here we will see those test vectors. So what you do here, first, reset the flip-flop. You resetted the flip-flop, and then D input D doesn't matter. X means 0 or 1, whatever, don't care. Q is 0 because you reset the flip-flop, and Q bar will be complementary to the Q. Then you release the reset. It means reset goes low. Then if the D is 1, then your Q is still 0. Because the clock is 0 at that time and Q bar is 1. But when you toggle the clock, when the clock goes 1, and then when D is 1, Q becomes 1 and Q bar goes to 0. This is how the simulation got finished. Now you have like different option. You can explore them on your own. Okay. So this is how you see that successfully we can use the online compilers to test and simulate our codes and do our design execution. So hope you found this model useful. If you do so, keep practicing writing code and then keep doing that. So if you have make some error, for example, let's say you have some typing mistakes here, okay, some typing mistake, and then you run, you might run into an error. We'll see that it is. So you see exit code expected received. So there is this error for sure. It is showing you the error, right? Compile two errors. Two errors have been reported. Okay, so you can see those errors later. So Control Z, and that's it. Click run again, and it will this time have no error. Done. No error. Otherwise, there'll be error. So this is how you do it. Okay. So stay tuned. Share this with others for more engaging content like this. Till then, wish you happy learning.